Hi everyone. So today I'm discussing about Rabi's atomic beam method for a determination of a magnetic moment. So here we have a principle as the method of involves reorientation of the nuclear spin. So in this principle, this entire method is depend upon the principle which is the method of inverse reorientation of the nuclear spin. So here nuclear spin nothing but the electron revolves around the orbit and our electron also revolves around its own axis. The electron revolves around its own axis, that is nothing but a spin. Okay, so here our nuclear spin is half. It is a half integral multiple. Okay, and the nuclear magnetic moment by the resonance of a high frequency and electromagnetic field and calculation of mu1. So in here in this method, what we are doing, we are finding a this entire thing is occurring in the nuclear magnetic moment by a resonance of a high frequency. The magnetic moment of resonance is occurring in the high amount of frequency and electromagnetic field and calculation of mu. Here, our entire goal in this experiment is to find out the mu. Okay, so what is the construction of this entire experiment? So here we are considering a lithium chloride substance, and along with that, here we are considering O is the thing, but it is a oven for heating lithium chloride substance, and we are taking three magnets and two are kept I mean A and B kept horizontal and C is kept vertical. Okay, so this is just a trial and error method where the scientist got a Rabi got the actual magnetic resonance. On that basis he kept this magnets. Okay, and along with that we are connected three pumps so that whenever this entire apparatus gets too much heated or too much heat is produced inside this, so this pump can cool that entire experiment. And along with that we kept a slit over here. Okay, this is all about the uh, construction. Once again I will repeat that we are taking a oven, okay, for heating purpose, and we are taking three magnets. A, B are horizontal magnets and C is a vertical one, and along with that we have a slit and we are using a three pumps, and lastly to detect the resonance we have the detector. Okay, this is the entire uh, construction. So what is the working? The working is the beam passes through three magnets A, B, and C. So see, when lithium chloride substance is heated in the oven, what happens? It start to release the electron. It start to release the continuous electron. Okay, so the electrons are passed through this magnets. First, it passed through the horizontal magnets and then to the vertical magnet. Okay. So after passing, what happened? It start to produce a resonance, which is detected in the detector. The translatory force acting on the magnetic dipole of the moment mu I is given by here. What happened when the electron was passed through this entire magnet? It forms the translatory force. It forms the translatory force that acting on the magnetic dipole moment. That whatever translatory force is there, that is so acting on the magnetic dipole moment, that is the mu I. So, which can be written as F is equals to mu I into dou V by dou Z. This is a very important expression which we are going in the in next derivation of this Rabi's method. So, just remember this F is equals to mu I into dou V by dou Z, which can be written as F is equal to G I into mu N, okay, mu I into dou V by dou Z. This is the thing. This is M I. This is a MI, where Gi is a nuclear G factor. So Gi is a nuclear G factor or a correction factor, and Mi can have a 2i plus 1 values with. So this whatever we are writing here, I know this can take the values of uh, 2i plus 1. Okay, here they have written m1 is equal to I comma I minus 1 so on to minus I. So how this resonates or how the entire thing is detected in the detector, that is shown in this graph. Okay, so this is a trajectory of a molecule dipole in the inhomogeneous magnetic field. Why we are calling inhomogeneous? Because we are keeping the magnets, one is horizontal, one is vertical. So this is inhomogeneous, which is not similar. It is slightly different one. Okay, so the graph is look like this. This is magnet A, B and C. Here dou H by dou Z. You can see the initially graph is increasing at a slit, nothing but the electrons are moved. Okay, when it reaches to slit, and after crossing the slit, the electrons are came down, decreasing. Okay, this is the thing. O to D. The molecular beam split up into 2i plus 1 different beam after emerging from magnetic A. In this case, I is equal to 3 by 2 for a lithium nucleus. So here the spin of the lithium is 3 by 2. The beam splits up into 4 parts. So here our beam is splitting into 4 parts, that is mi is equal to plus 3 by 2. Okay, so as we know the spin is plus or minus 1 by 2 plus or minus 3 by 2. This is written over here. After going through the origin, after going through the region B, the beams are refocused on the detector D. So uh, when this entire electron is passed through this magnet B, it is focused in the detector. It is passed through this, it is focused in the detector. Next we have the magnet B produces a homogeneous and steady magnetic field P naught. So here this B magnet what it do? It produces the homogeneous and steady magnetic field, nothing but constant magnetic field, and that is denoted by B naught. And alongside the magnetic moments of the molecules process about it, the alignment of a mi with respect to B naught is determined. So what we are doing in the further case is we are just seeing the alignment of mi and B naught, and we're determining its mi and B naught in the further case. The energy of the dipole in the magnetic field B naught is given by the, here what we are considering the energy of magnetic field, that is B naught, that can be written as delta U n is equal to minus mu y factor B naught. Okay, so this mu I can be written as minus G I mu n mi into B naught. So what we are doing, we are finding the energy. Okay, energy. So to find the energy, what we are doing, we are taking a delta un that can be written as minus mu I vector into B naught. This mu I, we can substitute mu I value as g I mu n into m. Just substitute over here, and we get delta un is equals to minus gi mu n m I and this. Okay, then the energy difference between the successive states of the different orientation of beam. So whatever we have, we took the energy, so we have to check the energy differences. So here the energy differences are just applied write the changes. Delta delta into mu n is equals to gi mu n b naught. Okay. So as we know from the Bohr magneton, we can write nuclear Bohr magneton, that is mu n is equals to Eh cross upon 2mp. Okay, that value just substitute over here. So you can see that this entire thing can be written as delta E. As you so uh, as we know, delta E is equals to h cross into omega n. This is the expression for the energy uh, in terms of the Larmor's precision frequency. In terms of precision frequency, the energy is given by like this. So just substitute delta E value is h cross omega L is equals to gi E h cross B naught upon 2mp. This h cross gets cancel. So remaining is omega L is equals to gi E B naught upon 2mp. Where omega, as I said, omega L is the Larmor precision frequency and mp is the mass of a photon. So finally we can write it as omega is equals to omega L, that is gi EB naught to mp. The value of gi can be determined by which fields of the value of mu I. So this can be determined by mu I value here, where it found here. This value can depend the we can find the gi. This is the entire thing about the Rabi's method. I hope you got this entire thing. Thank you so much for watching.